So let's continue. So last time we were looking at this problem, right? Where obviously, you know, we are right meant to use the result in the previous problem, right? Where it says that if a chain is doubly stochastic, right, meaning that if all the row sums and all the column sums are one, then the stationary distribution, right, is a uniform distribution over all the states. Notice, right, that here is kind of obvious, right, that the chain must be finite, okay? You should think about it. Basically, does this result extend to infinite state space? What do you think? Can we have a doubly stochastic infinite state space chain? Is it possible or not possible? The answer is right. It is possible. And I believe, right, that something like a symmetric random walk is doubly stochastic, right, in an infinite state space. But you see what happens there? What happens there, right, is that it is no recurrent, right? Simply because, well, you're dividing by infinitely many state. M is equal to infinite. So you get pi, right, to be the pi I to be zero for all I. So it's not a probability, right? So the balance equation, right? Pi I equals to pi j, right? Equal to sum of pi I pij is valid, right? For whether you have finite or infinite state space. The thing is, right? What conclusion do you draw from that? And right conclusion in the infinite state spaces, right? If they're all equal, then they cannot be, right? They have to be zero. So how would that be relevant? Well, that would be relevant in this question, right? Where, you know, I did propose, right, that let yn itself be the chain that we look at, right? And that actually is a wrong proposal, right? Because if I let yn be the chain that we look at, then yn will be an infinite state space chain, right? Because the state space, well, right, you just keep adding the sum of the row of the dice, so it keeps growing, right? But just to point out, right, why would that be wrong in the face of this problem? Because I could have done that. I could have got a different result, maybe. But the point, right, is that it is wrong because, for example, if I look at an infinite state space, right, like this, and this is where my analysis was wrong last time, right? If you look at, let's say the first column, right? What is the first column? The first column consists of pi1, right, for all I. What does that mean? That's a probability, right, of moving from state I to state 1. Well, of course, right, what do we represent by I here? I is a sum, right, of the dice, right, at the end step, whatever that is. So clearly, right, nothing can move into 1, right, because you have to add at least 1, right, to get there. So because nothing can move into 1, these are all zeros, right? So the chain yn, as I proposed, is a Markov chain. It's just not doubly stochastic, right? So basically, just to say that that was a wrong proposal, right? But I hope to point out why it is wrong, right? And so the right proposal, right, as Kathy pointed out, was to mod 13. And I guess that's obvious to most people, right? That you want to go finite, so you mod 13. And also, right, the word multiple of 13 is kind of really, right, kind of saying it. And what's the difference, right? If you mod 13, then, right, so something like this too, right? You have a 0 here, right? What happens is, let's say for a column, right? To add to 1, right? You could have a negative number, right? Adding to 1. Well, negative number here is, I don't know, right? In mod arithmetic, right? I don't know. Say mod -1 here is 12, -2 is 11. So there will be exactly, right, 6 entries that will add into 1, right? And all of them have probability 1/6 because the dice is fair. I guess, do we need the dice to be fair here? Yeah. What if the die is not fair? I think if the die is not fair, you still get the same. Wait, hold on. That's an interesting question. This is, of course, not a question, but what do you think? If the die is not fair, will this affect the answer? What do you think? So my initial intuition, right? I haven't checked this real quick because this is just a question that just popped up right now. Is still the same answer, right? Because you still have 6 entries, right, that add into 1, right? Namely the ones that, the sum 1 to, the before, right? Add 1 to 6 to get to 1. And they all add up to 1, right? Because these are distinct values. So the chain is still doubly stochastic if the dice is not fair, meaning the answer is still the same, 1/13. But that's where it's a little bit interesting, because you would expect that the dice being not fair would affect, right, the proportion of different sums. So why is it still uniform? The result is like that, right? Which is correct if my analysis is not wrong, but the intuition doesn't seem to fit. So I'm not sure my analysis is incorrect somewhere, or my intuition is not there yet or something, right? But right now, I feel like if the die is not fair, you still get the same result. Okay. Any question? Okay. Okay, I guess I could see it now a little bit more. Basically, because we're modding 13, the proportion, right? The combinations to get to 13 is probably similar to the combination to get to any other number. I'm not so sure. Anyway. Okay. All right, let's take a look at this. All right, so let's try to see. So we have the number of storms, right, in a good year and a bad year. And the weather condition, right, depends through. So first of all, right, let's just ask, what is the Markov chain here? Or what are we tracking in this problem? And so, of course, right, the question is about the number of storms, right? For Yn, right? Okay. And let's say we start counting from year 0, whatever, right? But what else? Is Yn a Markov chain? Is Yn itself a Markov chain?
No, the only Markov chain here would be whether it's a good year or bad year.
Correct, right? Correct, exactly. That's good, right? So if you know the number of storms in the previous year, meaning condition and Yn minus 1, right, it doesn't tell you if it's a good year or bad year, which is, right, here is a very interesting thing. And this is actually something along the line of a hidden Markov chain that indicator, right? Because you think about this is good on paper, but in practice, is the Yn, right, that we observed, right? And the good or bad year is not observed. This is actually human instinct, right? Or whatever. No, well, not really, right? There's something that we observe, behind the scene that we suspect that, right? There's a kind of a pattern of good year, bad year, whatever. But that's a hidden Markov chain, right? And that actually it makes, let's say, real life modeling much more interesting that way, right? Because whatever you observe is not really a Markov chain, but you suspect there's a Markov chain behind the scene, right? Usually kind of making up of things that are human concepts, right? There's no good or bad in nature, right? There's only a storm in nature. But we cook up this concept so that we can kind of put a pattern on it and, right, modeling how to kind of find the transition probabilities, for example, from good to bad, right? That's exactly the interesting question to ask. Anyway, right? But if we have that, then we have P, right? Which is a matrix moving from 0 to 1, right? Which is the good to bad, right? Good year is equally likely to follow by good or bad. So that's 0 moving, right, into 0, 1. A bad is twice as likely to follow by a bad. So I think that language is 2/3, 1/3. Do we agree? All right. So based on this, right, and we start out x0, right, is good. Wait, hold on. What the heck am I saying? So sorry. So I think I named 0 as a good, right, and 1 is bad, but I think it should be the other way around, right? Intuitively, 1 means yes, 0 means bad. No, right? So 2/3, 1/3. Sorry, no. Bad followed by bad, right? It's okay. I mean, my other one was not bad. It's just I want to kind of, stay with convention that 1 yes is good and no is bad, whatever, right? So x0 is 1, right? Which is good. Okay. All right. So how do we answer question A and B? Question A.
If you want the expected total number of storms in the next 2 years, we want the expectation of y1 plus y2.
Yeah.
Using linearity, we can just split that as the expectation of y1 plus the expectation of y2.
Very good.
And then we can condition on xn using law of total expectation, right?
Very good.
to calculate each individual expectation.
Good. Very good. Right, like that. Okay. And of course, right, we got what was it? 3 and 1, right? So something like probability of x1 equals to, if it's a bad year, right, you got 3 and then 1, right? If it's good, right? And similarly for the other one, right? Correct. And then finally, what do we do with these probabilities? We would extract it from the transition matrix. It'll be something like p square 1 1, p square 1 0, that kind of thing, right? Because we know that we started at a good year. Right? Any question about this? Okay, so how do we do part B? I guess that's easy. Well, so part B, what will we do? Let's talk about the idea here, right? Because I guess hopefully the execution is clear, right? Part B asks for what? Probability y3, right, is equal to 0. Right? And it's actually also equal to, right, the conditioning. Correct? And then you just write down the appropriate terms from there. Any question? All right, what about C, long-term average of number of storms? How will we do C?
Really quick for part
Yep.
B, when we're
Yep.
trying to get exact values for the conditional probabilities, we have to reference the Poisson distribution, right?
Yeah. So for example, right, it'll be e to minus this one, right? Will be e to minus 1, right? If you got the good year,
Mm-hmm.
and e to minus 3, right? If you get a bad year, right?
Right. Okay.
This probability Poisson 1 equal to 0 and probability Poisson 3 equal to 0, right?
Okay. Yeah. And then you get the marginal probabilities from the transition matrix. Okay.
Exactly. Yep. All right. What about part C? Part C is rather simple, right? Part C, the answer will be pi 0 times 3 plus pi 1 times 1, right? Where pi are the long run distribution or stationary distribution of the P matrix. Correct? That's it. That's a long-term proportion of the number of storms in a year. Any question about this?
Do we have to show the calculation or no?
You mean to find pi? No. who cares? As long as you state what pi is, right? You have to say pi p equals to pi. And I'm being lazy here, but the sum over pi equals to 1, right? Because again, right, this class is not about calculation, right? You want to do that, you go to linear algebra or low linear algebra, right? We all know you can do that. Well, part B. I mean, of course, for homework, you should find it, right? Because I think the homework has answers, but for exams, no. I'm not sure for homework I even bother to write down, but since you have tools at home, you can do it. What about D? D is similar to C, right? Where instead of 3 and 1, you put e to minus 3 and e to minus 1, right? Representing the probability of not having storm in a good year or a bad year, right? Are we okay? Any question here? All right, let's continue. Yeah, I guess before we go into this problem, right, just a comment on the previous problem that basically you see the whole point, right, is that even though we say explicitly from the start that y is not a Markov chain, right, but long-term proportion concepts still apply to it, correct? And again, when you think about it, it's not strange or anything like that, really, because the notion of long-term proportion, remember, as we define it as a sum divided by n limit as n goes to infinity, right? It's not limited to a Markov chain, right? Now, stationary distribution, when you think of it, may be a bit weird, actually, because stationary distribution is about when you are there, you stay there, right? But a non-Markov chain may not move sequentially, right, from a step to another. Do you understand? Like a Markov chain. But long-term proportion as a concept applies to non-Markov chain, right? So that's probably the conceptual thing to point out in this question. I mean, the calculations is very intuitive, right? But that's why, like, the long-term proportion concept, and again, right, going back to that YouTube video, not that I mean to or want to advertise for it, but I didn't even watch the whole thing, right? It's kind of boring to me. But I guess the big deal here is the notion of long-term proportion, sort of universal, right? You can literally apply to any process, Markov, non-Markov, who cares? Long-term proportion is a concept or is a question that's well posed. Whether the limit converges or whether it converges to a known quantity, right, is an interesting question to solve. But right, that concept doesn't have to be limited to Markov chain, right? It can be extended to non-Markov chain via some connection to Markov chain so that we can solve for it, right? So that's the conceptual connection I want to point out. Okay. All right, so now let's go to this one. Okay. So I guess the only thing about this problem is what? What's the big challenge here? The big challenge is to model the Markov chain, right? Whatever that is. And then, write down the transition probability. Besides that, right? The answer here is pi, where pi p equals to pi. Correct? That's all we do. Okay, so what is p here? Or let's not even talk about the specific numerical values yet, right? What are we looking at? What is the Markov chain? What is it tracking?
Can we just track the color of the ball? Because the color of the
Sure.
ball determines the next one.
Yeah, exactly, right? So basically, it's really a Markov chain of 3 states, right? Where 0 is red, 1 is white, and 2 is blue, right? And if this is a Markov chain, then pi p equals to pi, right? Is the answer, correct? So to just get it started, right? Let's just fill out one row, right? The rest we can just do it, right? So, oh, by the way, right? Let's ask with the description here, right? Which is what? Initially, a ball is randomly selected from the red urn and then returned to that urn, right? What does that statement supposed to describe?
The initial probability distribution, right?
The initial distribution, correct. Now, as far as the nature of this question is concerned, is that statement relevant, or does that statement have any contribution to the answer?
No, because we're looking at long-term proportional.
Exactly, right? So those are the connections right there too, right? So this detail right here just gets things going, but you could literally pick it from any other urn, or you can just start from a determined urn or determined ball, things like that. Right? The answer will always be the same. Okay. Good. So now, yeah, who wants to tell me a row? And once we verify it, we'll call it good enough and continue. Or barring that, maybe an entry.
If I'm not mistaken, for the first row, I have 1/5, 0, 4/5.
Okay. The 0 sounds interesting and probably not easy to verify, but 1/5,
I agree.
0, 4/5. Thank you very much. So, River, if you don't mind, could you very quickly explain these 3 entries? I guess the 0 explains itself, but go ahead.
I quite literally just took the proportion of balls in the urns because it's random. There's no, I just did
Yeah,
math.
right. And I think that's really it, right? Because it's very easy because this transition proportion, because right? You come from the blue urn, so right. I mean, that's it, right? That's how you got the next distribution of the color, correct? So there's nothing mysterious here. So yeah, right. Even though the urn descriptions might seem very crazy or complex, it's very a simple problem. Any question? Okay. Okay. How about this one? This is the dilemma people always have when they have too many pairs of shoes. Okay. I hope that you finish reading the problem because as far as my memory goes, the first time I read this problem, took me a while to even figure out what the heck is going on, right? But obviously you have less time than that. But after this sinks in, tell me, right? So the question is clear, hopefully. But what the number one question here, right? And once you realize what the number one question is, things will become a bit clearer and easier. What is the Markov chain here? Or what should we track that would be helpful to solve this problem, right? Because they're like in a modeling problem, a real life problem like this, you want to call it real life. The main thing or the main difficulty is that more than one thing to track, right? Or the thing to track is probably not obvious. And so you could track the wrong thing. That's all there is, right? But once you track on the right object, things should start developing on its own. Okay. And the answer is kind of like suggests itself. So here, right, what should we track? What's the right Markov chain?
Here's my proposition.
Yep.
So if xn is the chain, then xn denotes the number of pairs of shoes, which can range from 0 to k, at the front door. And I'm saying that without loss of generality. You could also do the back door, I guess, at the end of day n.
No, that's very good. But let me play the, I don't know, the devil's advocate here
Okay.
and be confused. There are two places, right? You mentioned front and back. What do you want me to do?
So, I mean, okay, if I choose the front door to be
Yeah.
relevant to the chain, then I know that the back door is just if I have say I, then you know the back door is just k minus I plus 1, right?
I thought just came as I, right?
Okay, or
Isn't it? Because the total number of shoes is K. So if it's I there, then it came as I the other one.
I think the reason I'm confused is because there's also the barefoot case, which is like your 0th state.
No, but no. Yeah, but see, what are you tracking? You're tracking the number of shoes, right? Once you're clear on that.
Oh,
Or
wait,
total number of
yeah,
shoes.
yeah, yeah. Okay, yeah, the number, okay, yeah,
That's fine, right? Yeah, of course. Then zeros is a zero number of shoes, and there are n pairs on the other side, right? Or k pairs, right? So good. No, everything you say is spot on, right? So the thing we want to track, let's say xn is number of shoes, right, by end of day, whatever, at front, right? And that's all we need to track because let's say yn is the corresponding one, is k minus xn. So that's it. Once we figure out xn, we want to know what yn is. Do we understand? So that's the key, right? Or well, let's say that's not the key yet. What would our suppose we do some magic here, right? Of course, with the p and everything like that. What would the final answer look like? What would the final answer look like? Of course, right? There's some p and there's some pi and blah blah blah, right? But what would the final answer be?
Would it be um pi 0 plus pi k.
Almost. Almost. Very good, but almost. I believe there's a 1/2 there, no? Because pi k is when he then, right? Well, what by pi here, we just focus
I
on the
see,
x,
I
right?
see. Yeah,
The y is in the background, so we are not even looking at it. We're just saying the y is obviously there, right? And then this is exactly where it matters, because right, pi 0 is when he runs at the front door, right, and encounter x, and pi k is when, you know, the front door has k pairs, but he runs at the back door, right? But then 1/2 each. So, all right, any question? And you see, once we figure this out, right, the rest are just technical stuff. Because, okay, someone tells me what the P matrix looks like. There is 0 to k, right? But what's Pij? Describe Pij to me. You might have to look at the boundary case, right? Namely, when I equal to 0 or k, and j equal to 0 or k, right? But that's how you describe it. The boundary case may or may not be there, meaning that it follows the same pattern as anything else. But there could be boundary cases, so always watch out for boundary cases in this kind of problem. What is Pij? Okay, so to let our imagination going, right? First of all, it's clear that here ij must be at most different from 1, right? I think that's it, right? Pij is 0 if I minus j is bigger than 1. Agree? The transfer is only 1 pair at each time. Yes? At most. So let's see here, right? What's P0, 0? And what's P0, 1? Right? These are the only two possibilities, right? Can someone tell me what that is?
P00 would be 1/4, I'm guessing.
Guessing or no?
My educated guess.
Okay, fine. Explain, and then we'll see. Why is it 1/4?
Okay, so if you have 0 shoes at the front, then you're leaving the front door with probability 1/2, and then you're
Yep.
picking up, you're going running barefoot, and then you're returning to the front door with probability 1/2, and you're returning 0 shoes. Right. So
What if you return at the back door? If you return at the back door, then
well, it doesn't change anything.
right. So
It doesn't really
right.
matter.
So you want to modify your answer? So what's P00?
Oh, 1 minute.
I believe it's 1/2, right? From what we just said. Because right, it only stays 0 if he leaves at the front door and run barefooted, right? Which makes sense.
Yeah, that makes sense.
If he leaves,
Doesn't matter which way he returns.
well, hold on, but I could see the 1/4, right? If he runs at the back door, then it only becomes 1. Oh, no, right? So it's actually 1/2 plus. So it's actually 3/4 here. So actually your answer actually is swapped, right? So it's 1/2 if he runs out the front door, because it doesn't matter where he returns, he just stays there, right? But if he runs at the back door and returns the front door, then he will deposit a pair of shoes there. So it's 3/4. Agree? Oh wait, what the heck am I saying? Stupid. Sorry. Say sorry. The other way. If he runs at the front door, doesn't matter where, right? Where he returns is 1/2. But if he runs at the back door and return at the back door, then it still stays 0. Correct? So it's 3/4. The only time it moves up to 1 is when he runs out of the back door and return at the front door. So that's 1/4.
I agree with that.
Yeah. Sorry, I had that in my mind, but I said it backward. Okay, any question? So I hope then we understand what PKK is and PK minus 1K is, right? What's PKK?
That just generalizes, right? That our intuition here for the 0, 1 case, or 0, 0. So it's 3/4 and 1/4?
I'm afraid not. Probably
Right.
it's the other way around, right? So PKK here sounds like 1/4. Because the only time it remains the same is if he runs out the front door and return the front door. Oh, wait, hang on. No, if he runs out the back door barefoot, sorry, no. So PKK here is also 3/4. Yep, you're right. And this 1/4. Yep. Are we okay? So for the remaining i's, right? Tell me what PII plus 1, and PI minus 1i is.
It's 1/2, 1/4, 1/4.
Sounds about right. So you mind explaining, Peter, why PI is 1/2?
Yeah, it would be 1/2 in the situation that it would stay the same if you go in through the same place that you entered, which is equal probability. So that's leave front, come back front, plus leave back, come
Leave back, come back.
Yeah.
Which is 1/4 each, so that's 1/2. Very good. And the other two cases is like leave front coming back, or leave back coming back front, right? Which is 1/4 each. Very good. So 1/2, 1/4, 1/4. Okay. Any question about this? And then that's it, right? The answer is 1/2 pi 0.
Which
That's right.
one corresponds to which case? So PII plus 1 corresponds to which case?
I'm lazy, but it's a quarter, right? It doesn't matter. But so
Okay.
I plus 1, right? If you really want, because it's 1/4, so who cares? But okay, let's see here. So I plus 1, right, would be you increase, right, a pair of shoes at the front. Well, that only happens if you leave the back and come back in front. That's it.
Okay, I'm happy. Thank you.
Yeah, sure. No worries. But once I see the 2 1/4, my brain just shut down and doesn't want to work anymore. But we're good. All right, any question? All right, cool. Let's move on. Okay.
Quick question regarding the previous question, right?
Sure.
It's equally likely to leave from the front and then also return to the front, or it's equally likely to enter
I think so.
and
Right.
exit
I think
both doors. So if there was a bias, like you're leaving from the front 3/4 and stuff, it would be a lot more complicated, right? But it's still the same approach.
no. Well, so it will change. I disagree with a lot complicated.
Okay.
Because what change? I think all the structural problems still stays the same. Namely the xn, the yn, and the answer, right? The final answer.
Right.
I think all those are the same. The only thing that's different is the P matrix, right? But even the boundary cases, the movement, right? Only one step at a time, like a random walk, still right? So it's actually like a reflected random walk, right? A random walk that bounce back at the boundary case. And the back front analysis still holds. It's just the combination of numbers are different. So I would not say it's a lot complicated. It's just slightly more interesting.
Okay, it's just a
right?
variation.
Exactly. Okay, so let's take a look at this shuffling problem. And right, again, the question, right, I hope you see the pattern here, at least for this type of question, right, is what is the Markov chain, right? What are we tracking? Because, getting that down correctly will basically, right, means other part follow naturally. What should we track here? What are the space?
I would say X sub t is the current ordering in a linear sense
Yeah,
of the cards at time t.
correct, right? Unfortunately, because of the answer here, right, it's kind of obvious that there's n factorial. Permutations, right? There's nothing really we can do about that. Meaning it's a huge matrix, right? But I guess the thing here is they're not even asking us to solve for pi. They only propose, right, what the pi is. Correct? Because it's uniform. That's what they say, right? We just have to explain why. So now, well, why do you think that's the case? Why would the long-term proportion, or I guess the stationary distribution, right, is uniform here? And by the way, right, I guess let's ask this. Even though I guess the three concepts are the same, right? This is a good question. This is a good occasion to ask. In this particular question, which one of the three concepts we talk about pi, right? Pi has three possible interpretations, right? Stationary distribution, long-term proportion, or limiting distribution, right? Which one do you think is the one that is aiming at in the shuffling problem here? And what would make sense in this context? I mean, I'm not saying none of them make sense, but what would be the one that people look for in the shuffling here? So here, right, I would argue that it is the limiting distribution concept that is the most relevant here. Okay? Because first of all, right, stationary distribution, do you care? You don't, because you may not start out with a stationary distribution to begin with, right? You care for long-term proportion. Well, you do not need to know, right, in the long run, how many times in a shuffle, right, you get this kind of permutation, right? That's not what you care. You care that when the card is dealt, right, that is well shuffled. Agreed? You care that when the card is dealt, it's well shuffled. So what that means is you care that if you shuffle a lot of times using this mechanism or whatever that, you know, the well shuffling mechanism is, then when it starts being dealt, you can be confident that, right, the deck is well shuffled, more or less. So here, right, in this particular case, the limiting distribution is the relevant concept, right? The two other ones, long-term proportion and you know, station distribution actually are not relevant. I would argue, right, in terms of what people are looking for. Okay, so that's just a comment on this. But anyway, right, how do we get to the answer that's uniform? Well, let me give you a hint. Have we seen any uniform stationary distribution so far in the problem set?
If our transition matrix is doubly stochastic, then we have
Correct. So I'm not saying that doubly stochastic must be the only one, but it's highly, right, suspicious that we could sneak that in if we're lucky, right? So a good guess is somehow the P matrix that we're dealing with is doubly stochastic. Well, is it? So if we can prove that P is doubly stochastic, we're done.
Yeah,
Check the
this one definitely is doubly stochastic because it has a 1/n probability of going to the n permutations where each one of its orders is just the first one on the next ordering. So if you sum all those 1/n's up, it's 1. That's a very like
No, I know, right? And that's where things, right, of course. But that I think I got what you say, right? So basically notice, right, for the doubly stochastic, what's the main challenge? The main challenge is to show the column sum equals to 1, right? Because the row sum has to be 1 to begin with. All right. So your main challenge is to show that the sum Pij summing over all I is equal to 1. Right? And now remembering what Pij means, that's moving into J from I, right? Which is the opposite of what we usually think about, meaning moving from I into different J's, right? J now is fixed, and we look at the beginnings, right, or the starting point as changing. And now, right, what River would say is there are only n possibilities, right, with options for I, let's say, probably 1 for n each, right? If we can argue for that, then we're done, right? River, that's what you're trying to say.
Yeah.
Okay, now can you, once I say that, could you elaborate why there are only n possible positions for I? Oh, sorry, n possible options for I. Remember, I here stands for a permutation, right?
My intuition was that given the ordering of n cards, in the process you pick one of them and then move it to the first position. So there's only n, given n cards, there's only n ways you can move it to the first position.
No, yeah, or I would put it this
add
way. I
on
know. I'm sorry.
to add on
You
to
know,
what River was saying.
sure.
There's
Sorry.
only
Sorry. I know you guys are very excited about this, but sorry. We are at time, so I hate to change the schedule. So let us go back to this, right? I promise we will. Let me give you a quiz real quick, right? Because of the closing time of the quiz, I hate to go and change it. Sorry about this, all right? So let us, okay. Give you this question, part A, okay, as a quiz. Is that okay? And then we'll continue back at 35. Is that right? Is that right? Okay, any question? Okay, sorry about cutting you guys off. All right, let us continue at 11:35, okay? Okay, so let's continue, right? So, yep. Anyone wants to continue explaining the n options for I here? Well, so right, I guess basically, so here, right, it is one of those things where you try your best to describe the situation. But basically, right, because of the mechanism, right, of the shuffling, meaning that you, right, you select a card randomly and then put on top, right? Basically, in terms of permutation, what you're saying is you just switch the number, right? Switch the entries of two positions. That's really it, right? Basically, the mechanism is that you permute I and 1, right? And leaving everything else the same, correct? So from that point of view, right, you can only move from one position to another position. So yeah, so I guess probably Driva would say something like this before to begin with anyway, right? But basically from this description, right, there are only n possibilities you can move into, or right from that point of view, there are only n possibilities you can start from, right, for any desirable target, right? And the probability of that is 1/n because you just select a card randomly. So I'm not sure I'm doing a better job than River here, but right, just kind of like maybe try to point out as much details as possible. Okay. Any question? All right. So how about this? Right. So I hope by now the scheme is clear, right? The questions are, what's the Markov chain? Can we write down the transition matrix? Right. By the way, right, there's one crucial step that we skipped over in all these problems that in reality must be checked. And I don't want to make it sound trivial, right? So I want to point out that, so step one, right, write down the Markov chain and decide what the Markov chain is. And step two, write down transition matrix. Those two steps are very important, right, in terms of thinking about solving the problem. But step three, which we skipped over, is to check if the chain is ergodic. If you're looking at the limiting distribution, like the previous one, the shuffling problem, or check that it's positive, recurrent, and irreducible if you're just looking at long-term proportion and stationary distribution, right? I guess if you solve for pi p equals to pi, you already kind of discover that anyway, but we kind of skipped over it. So, right, the nature of solving for pi p equals to pi might reveal something to you too. But right, maybe you won't, because these days and age, right, you could just throw it into a solver, right, and ask to give me a pi. And it could give you a pi, right? And you may not notice that there are two possible pi's because the matrix is reducible or something like that, right? So in investigating the structure of P, right, to make sure that the condition is met, and that's subtlety, right, between limiting distribution where it requires more, it requires the chain to be ergodic, meaning aperiodic, right, versus just long-term proportion where it's just positive, recurrent, and irreducible. right? It's something you want to pay attention to, right? Which we don't do here because basically all chains are like that, right? Satisfy those conditions, okay? All chains in these examples. But, all right, so, right, decide what the Markov chain is, decide what the transition matrix is, assuming we can solve for pi, how is the final answer expressed in terms of pi? That's really the scheme, right? So for this question, right, what is the Markov chain? What's transition matrix? The Markov chain would be the position of the flea, right? And the transition matrix would be how it moves from, you know, one position to the other, right? As given by the description, right? And A would be pi. Well, but let's just discuss B real quick, because I think, right? So writing down P is easy, right? But then suppose you have the matrix P and the pi, then what would the answer be in part B? So here, right, I guess depending on how we label this, right? But if we label increasing order as clockwise or right, then counterclockwise is decreasing order, right? Let's say. Then basically, right, you start, so it's really, of course, the proportion of time you start at each of this, let's say at pi 1, right? So you make a counterclockwise, so you move from 1 to, wait, hold on, sorry. Did I say it wrong? I guess, yeah, I said it wrong. Clockwise is increasing order, right? See, I don't look at the clock that often these days. And then counterclockwise, right? So you would do P13, right, for counterclockwise, and then move back from there. And then so on and so forth. Does that make sense? So it's just a elaborate writing down of 6 transition probabilities with the long-term proportion, right, staying at the starting position to begin with. Nothing more than that. Any question?
Couldn't there be something with Q? Like suppose you start at vertex 1.
Yeah. So I
Then
guess
you
the
want to go from
P13 here.
Q13. You want to
some of these would really have to do with Q, right? Because when I write P13 or P31, that one of them have to do with Q, right? But so the transition matrix, when you write down, right? For example, 1, 2, 3, 1, 2, 3, right? You clearly cannot stay from 0 to 1. You cannot stay at 1, right? 1 goes to 2 with probability. You know, this is clockwise, right? So P, and right, we would just write that, correct? But that's Q.
I guess
So
my only question is like the first term in the sum, right? Shouldn't it
yeah,
be pi 1 times Q13 because you're going counterclockwise once and then 5 consecutive clockwise. So P3,
no. I would.
P1,
I'm
2,
not so
3.
no, right? Don't confuse with the Q here. The Q here is just a cute, right, writing of this. And by the way, right? Oh, I see. So I see, because it says a clockwise vertex. Okay, so no, but I think no, I'm fine, right? Clockwise. So 1, 2, right? I'm good.
It's like a directed
And
graph. So going clockwise is a P and then going
no, but
counterclockwise.
I think no, but I think you are kind of
Okay.
confused between the two notations. The P here is, or the Q here is really little p, little q, and they are attached to the vertex itself, right? While here, this is a capital P representing the matrix entry.
Oh, I'm sorry. Never mind. I was
No,
thinking.
no worries, right? And so at this stage, I am beyond caring about how you write down a P matrix as long as you write down correctly. And that's where you can nitpick about, okay, is that little p entry there, whatever, right? But as long as you write down the big matrix correctly, then the direction of movement must follow my flow, right? Of graph, whatever you want, correct?
Yeah, I completely agree. I just thought the big capital P was a little p for a second.
No.
So it's
And then
okay.
also notice, right? This one only has one entry while mine has two entries, right? All right, we're good? Okay, let me just see how many problems are there. All right, cool. Let's continue. All right, let's take a look at this. I think this should be a quick answer, right? Because what do you suspect about this transition matrix? I think it's doubly stochastic, right? Because it says, basically, this is a matrix where all entries are 1 over 5, right? Isn't it? So the limit distribution is 1 over 5, which is a stationary distribution. Or wait, no. Yeah, it's 1 over 4, right? Because it doesn't go back to itself. It doesn't matter, right? But it's still doubly stochastic, right? So the limit distribution is 1 over 5. Are we okay? Any question about this? Let's check real quick. Oh, wait, no. You know what? I guess I'm not awake. I'm so sorry. Sorry. I'm not even reading. This is only from 0 to I minus 1. So it's actually a triangular matrix. Sorry. I'm very sorry. So 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, right? So that is given. And then let's say, no, sorry, P0 is guaranteed to go to 4, right? Okay, and then I think 1, and then 1/2, and then 1/3, right? And then 1/4. Like that, right? Sorry. So this is the transition matrix. And they ask to solve for pi, right? So, I mean, here's where the question is, can you quickly solve for pi? Or observing this structure, is there something you can do to solve for pi? Well, let's see here.
Can you use bootstrapping?
Yeah, it's just really a structure, nothing crazy. Yeah, so I guess for this question, there's nothing really intuitive, nothing conceptual here. It's just solving a system. Yep. Okay, any question? Yeah, sorry, I misread this question. Okay. This one should be easy. Right? Because basically what happens is, right, if pi p equals to pi, then pi q, right, which is pi p k times, right? Well, pi and then, by induction, right? So there's nothing really to talk about. Correct? Any question? I guess we already talked about this, right? Basically, it's just using the balance equation, right, to show that the the symmetric random walk, right, is no recurrent, because basically all the pi must be the same by the symmetry of the symmetric random walk, and therefore, right, if they sum up to one, if they're all the same, and then it's impossible, right, for them to sum up to one, basically, right? They must all be zero. Okay, how about this? I guess here, right, it's just basically trying to interpret what it means, the question. So we can write down the transition matrix, right? And we can solve for pi. Now, what is the question being? What is the final answer in terms of pi?
This one should be doubly stochastic, so the pi should all be 1/12.
Okay, yeah, but is the answer about pi? That's the question. What is the final answer here? What are we looking for? The average number of steps returned to the starting position. What does that sound like?
The expectation of VI, where I is the starting. Piece of I.
Correct,
Yeah,
but it's
Or
not expectation of VI, right? Expectation
VI
minus 1, right?
Yeah.
Because the number
And-
of steps to return. Good,
Yeah.
yeah, and what would that be? right? So it's expectation I, right? Vi minus 1. And what would that be? What's the identity? Oh, sorry. Actually, you guys, no, sorry. No, actually, no, sorry. Kathy's answer is wrong. Kathy's answer is wrong. No, it's not that. It's not VI, right? Because VI is what's paid out loud. VI is the number of visits to state I, right?
Oh, not the
And
number
by the
of
way,
steps.
yeah, and by the way, right, in a recurrent Markov chain, expectation IVI is
Infinite.
infinite. Yeah, right. So no, it's not the answer. What we're looking for? EI of
TI.
TI, correct. And what's the connection here?
Is that since TI is the first return time, the expected value of the first return time is just mean number of steps to return back.
No. Yeah, but what? How would we give the final answer
Oh,
in
yeah.
terms of?
In terms of P, I'm not sure.
It's the sum, right? The in
No, the sum is VI.
oh wait, never mind.
All right, you guys forgot that. And that's it. So the answer is 1 over pi I. Right? Again, why? Long-term proportion or long-term frequency is 1 over period, 1 over average period. So the answer is 1 over pi I, wherever you start. So 1 over, so actually it takes on average 12 steps. We're good? I guess here my notation is wrong, right? It's EITI. All right, any question? Okay, so this is a variation of the shoes problem, and I think this has the exactly what Kathy was asking, right, about the different probabilities, I believe. Okay, so I think, right, basically, we have seen the shoes problem before, so let's not really, right, spend a lot of time on this. What's the scheme here? What's the Markov chain? The Markov chain would be either the number of umbrellas at home or number of umbrellas at the office, correct? Pick one, doesn't matter, right? So the proportion of time the individual gets wet, right, would be pi 0 plus pi, how many umbrellas you have? R or something, right? Plus pi R, right? And then so part A, right? XT is just, let's say, number of umbrellas at home, right? And oh, so there's actually, of course, the whole kind of thing where if it rains or not, right? So I guess for part, to answer part B, you would want to write down the P matrix, right, for part A, right? where it goes from zero to R, right? Okay. So again, right? He would kind of bring an umbrella back or whatever, right? Depending, but now the probability depends on the rain, right? The rain condition, right? It rains at the beginning and end of the day, probable peak, right? So there are two rains possible in a day, right? But so for example, what's P00 and P01, let's say, right? And then the other ones, and then we'll see. What's P00? So he has no umbrella at home, right? He will not have any, so of course he would go out wet, whatever. He would go out without umbrella, right? So he would come back, right, with an umbrella only if it rains. So I think this is 1 minus P, right? And then this is P. Agree? Similarly, right?
Wait,
P,
I have a question.
yeah, go ahead.
If P is the probability of it raining,
Mm-hmm.
then wouldn't it be P00 equals P? Because it,
I guess from the description though, right? So this is at home, right? Or whatever, right? Let's say at home. So he leaves home in the morning, right? So he has no umbrella to bring, right? But then so it was at the office, he has our umbrellas. He will bring home an umbrella if it rains at the office. That's all, right? I think that's my analysis. So he will not bring home an umbrella if it doesn't rain. So that's 1 minus P. Or conversely, right? P01 is only when he brings an umbrella home from the office if it rains. So that's P. Do you agree? Or still don't agree?
I'm still confused, but I'm just
No,
gonna.
go ahead. What is the what
I
do you
have,
have in your mind? What do you have in your mind in terms of this picture?
I just have in my mind that he's at the office already,
Yeah,
not having taken an umbrella.
yeah,
It's raining, and then he goes
yeah,
home because it's raining. Then he takes an umbrella home
yeah,
with probability P because it's rain.
yeah,
Probability P.
yeah, yeah,
Oh, but that's P01. I understand.
yeah. Are we okay now?
Thank you.
Sure, no worries. This can be a little bit, circular things. All right, cool. So PKK will be, or sorry, PRR will be, and RR minus 1 will be.
That generalizes, right? So 1 minus P and then P.
I would run the argument again just to make sure.
Okay.
So let's run RR minus 1, right? He will lose an umbrella, right? If it rains at home and it doesn't rain in the office. Agree? That's the only time when he lose an umbrella. Yes. So the other one would be this. So I'm not sure about generalizing. I think that's that. Do you agree?
I agree, yeah.
Mm-hmm. So what about the other cases? PII will be what? I think p squared plus 1 minus p squared, right? The conditions are the same at both places. That's why it stays the same. You know, bring umbrella to office and home, or did not bring umbrella back, right? You would lose an umbrella if it rains at home. So I guess both of these are this. Right? Changes one different conditions at home and office. Okay. Any question? And so, right? Sorry, any question? And so, right, normally solving for this for pi probably is painful, but that's why this problem is helpful, because they propose this to you, right? And this is probably where, I guess, for this kind of problem, if you have to solve it for on your own, is the technique of guessing would be very important. Now, I have to admit, right, I'm just saying that in a vacuum, right? Because if you ask me about the guessing for structure of pi here, I probably would not be any better than you, right? But what I'm saying is, right, taking a clue from the hotel problem, right? Like, you probably don't want to solve for this with brute force, meaning just set up the set of equation and see what you can do. Sometimes guessing, right, the structure might help, but where does the structure come from? Right, in this kind of problem, I'm not so sure. But another thing to notice, right, is that pi 0 here is not the same as pi r, which further reinforces the idea that it's not symmetric, right, at the 0 situation and the r situation. Okay, but that's all. With part B, you just have to show that the system of equation holds, right? Pi I, pi j. You have to show it holds for 3 places, right? Where j equals to 0, j equals to r, and j not 0 and r, right? Because the system will be different at this row, and at the row in between. Are we okay? But you just have to check the solution. And part 3, right? Well, just basically, right, solve for a optimization problem. Any question here? Okay. And that's it. That's all we have for this problem set. Okay. Any remaining questions you have? All right. So let me tell you what I plan to do next. So as far as the program goes, the last topic I want to round off, right, Markov chain, is this one, where, right, basically it's about computing Fij for general INJ, the probability you eventually move from, a state to another, right, one state to another. Notice that we have done something like this, right, in the transient, this non-unsymmetric random walk, right, or the gambler's ruin. So this is like a systematic way to do so. And why do we care? And why do I say this kind of round off, right, the program of Markov chain? So the way I see Markov chain, right, is a very deep topic, by the way, right? You look at the textbook, there are some sections after this. But the way I look at it, right, is you need to know what Markov chain is. You know what Markov property is. You need to know how to model with Markov chain, right? And then you need to know how to compute path probabilities. Those are the basics. And then, right, we move on to the long-term behavior, classification of states, law of large number for Markov chain, that kind of thing, right? But the program there, right, is hanging on the assumption that a chain is irreducible, or at least that's a structure, right? That's usually assumed. And so, of course, right, in real life, chains are not irreducible, right? Chains have different classes. That's why we study classification of states to begin with, right? Classification of classes. And so the complete picture is, right, you have different classes. If you're in a transient class, you will eventually, right, with probability 1, be absorbed into one of the recurrent class, right? And then once you're in the recurrent class, then you just use the theory of the irreducible Markov chain with respect to a recurrent class, right? Because then, right, the Markov chain effectively is just a recurrent class. But before that, if you have more than one recurrent class, then you want to ask, okay, what recurrent class will I be absorbed into, right? Like the gambler's ruin problem. And so, right, to find that is exactly the purpose here, right? To find the Fij where you get absorbed into different J in different recurrent class, let's say. However, right, I mean, we are already right, only have like about 2 lectures, right, left. And beyond this, there's like a Poisson process and Brownian motion, right? Not that it must be covered, because my philosophy is more depth, right, than breadth, meaning that if I show you a lot and you have no idea what I'm talking about, then what's the point? But either way, right, I think we have done enough here. So the lecture slide is posted, right, you know, on Canvas. So if you're interested, you can take a look. We won't go over this like in depth, right? But I think that this is a good topic to take a look at to round off everything if you're interested, right? But as far as what my plan is, I still want to show you a bit of, right, Poisson process and Brownian motion as like the other prime examples, right, of stochastic processes. So let's move there, right? And we'll skip over this lecture. All right, so the first thing, right, or the next one in the agenda is like Poisson process and queuing model, right? These tend to go together. So let me kind of give you a brief overview of what's going on here. So the number one difference that you should recognize, right, or the way you can systematically schematize the stochastic process is the following. Stochastic process, right, is about time and space, right, and randomness. So time, you ask, is time discrete or is time continuous? Is space discrete or is space continuous? Right? That already kind of schematized the stochastic process to different classes, right? Markov chain, what we've been doing is discrete time, discrete space. And so you see that's kind of the easiest thing to start out with, right? And that that's why matrix can be used to control the structure, okay? And you think matrix hard? Well, wait till you see these kind of things. The next step, right, is continuous time, but still discrete space. So notice we're moving to continuous time. Time will be a continuum. So there you have no matrix to help you out, right? Because you don't have a next time step. So that continuity of time is already implicit, or is the difficulty, which may be not explicitly pointed out when you move on to this topic. But space is still discrete, meaning, right, you still move up and down at some discrete number. Like, you know, that's why queuing models, right? How many people you have in a queue, how many arrival events you have, things like that, but in a continuous time, all right? Next step up would be continuous space-time, and that would be Brownian motion, where space, right, so the Brownian motion will take values in a continuum of space values, like an interval, okay? And by the way, right, something like analysis, like real analysis is lurking in the background. Not here yet, because, right, you still have discrete state space. So at most you have like step functions, so not so bad, right? But still the continuous time is the challenge. But Brownian motion, right, will have analysis behind the scene because you have continuous time and space. And so the topic of something like stochastic analysis, right, comes up. All right. Anyway, so point of bringing that up is because right here, right, we're dealing with continuous time. Therefore, right, you have to kind of start to control the structure of time a little bit better. You need to have a language to describe it. All right. Before, again, time is discrete to the next point, blah, blah, blah. Now we need the structure of time. And for queuing model, right, the favorite structure to control the structure of time is the exponential random variable. Must you do it? Must you use it? Answer is no. And you should pose that question, right? But the exponential random variable is the good starting place. Why? Because it has many, many nice properties that help the calculation and the thinking easy. Okay. Namely the memoryless property and the combination of the minimum. Okay. But then, of course, right, from the exponential structure, you don't want to stay there because different models may not satisfy that assumption. So you want to generalize it, right, to the non-constant rate. So the topic hazard rate or the hyper exponential model comes up. And of course, now then we can put all the exponential clocks together and look at a queuing model, right? But so this lecture is queuing model, but another way you can put it is everything you want to know about exponential, everything you never know that exponentials have, and more, right? So you probably will see a lot of properties of exponential random variables that you may not know that exists out there. Okay, so right, so yeah, this is just kind of explaining, right, the importance of exponential random variables. That if you look at Poisson process, which we'll look at the next lecture, then the inter-arrival time, right, like the tau I that we've been harping on, right, in the previous one, or tau ij, the time you move from one to another event is an exponential, right? But well, with the Poisson process, you can only move up, meaning only from I to I plus one, right? You don't move down, you don't move horizontally. So basically, right, the time to move to the next event from I to I plus one, the waiting time, right, that TI that we've been looking at, sort of, right? It's not return time, it's a time to the next stage, will be exponential random variable, right? And I guess if I fail to mention it, right, the exponential random variable is a continuous random variable, right? That's what is continuous time, right? And yep, just re-emphasizing, right? That is a building block of Q model and stuff. Right. So let me pause here. Any questions so far? Okay. So here is the memoryless property, right? That, how should you read this? Basically, right, it says that if so X or T here, right, doesn't matter, represents some kind of time duration, right? That's the survival time of a person, the survival time of a device, the time you wait until something happens, like a customer arrives, right? So X bigger than T means you have survived that long, you have waited that long, right? And then T plus S, of course, represents the extra, right? The time beyond T, you still have to wait. And then this calculation shows you that, well, it's the same as the unconditional probability. But of course, right, the unconditional can be written as X bigger than S given X bigger than 0, right? This is true for all exponential lambda. Okay. So basically, right, that if you model something as a memoryless, right? Well, so there's two aspects of things here. We claim that an exponential lambda has memoryless property. And then the reverse thing is the only thing that has memoryless property is the exponential. Okay, we'll look at it. But basically, right, just to point out that the memoryless property is very nice in calculation, makes things very easy. Because you basically, right, notice this is exactly the Markov property-ish, all right? that we look at in Markov chain, right? It's not really Markov property. You have to be careful here because language can be confusing. But notice, right, what's Markov? Markov is, right, basically given the current state, you do not have to remember the past, right? All the past is irrelevant. So from that point of view, right, if you look at this, it has that taste. It's not the same, okay, but it has that taste. So the memoryless property here is, let me just say, closely connected to Markov property, right? Okay, but there you go, right? Basically, the clock, right, says that if you have waited, right, if you have survived until 10 years, then you look at the extra time beyond that year. It's as if you are renewed. So some of these are called renewal time too. You're renewed, right? And again, right, human life doesn't seem like that, right? I am 40 years old now. I don't know if, or more than that. It doesn't seem like, right? The next 2 years of my life is the same as when I was 20 years old. But so it doesn't seem like that, right? So I have memory, right? But something else may not. But this is where, right, the exponential may or may not be adequate, right, for your modeling, right, purpose. And you have to pay attention to it. But it's nice, and you want to know what you're committed to when you use the exponential clock. All right. So, right, the consequence of memorylessness is that, right, conditional expectation and conditional variance is a walk in the park, because, right, it just goes back to itself. So this is very nice to do calculation, right? And that's why, at least I suspect it's a sneaky reason why exponential is a building block. But of course, people are honest, right? They move on from the exponential model when they do things. But let me. I think I cut off here, right? So this, of course, right, is expectation of x. This quantity right here is expectation of x indicator function that x is bigger than t, right? This is the expectation of x knowing, or and. So this is the word and, right? And this is condition, right? So this is exactly the and or. Oh, sorry, and versus if, right? That I think I mentioned on day one. Okay. But let me just kind of mention one more thing, and then we'll continue next time. That basically regarding the exponential clock, right? You see this word thrown in around the MMK model for queuing, and then maybe something like GMK. So the first one is about the arrival model. The second one is about the service model, service time model, and this is how many servers. Okay. So MMK means arrival is modeled as a Markov, whatever that means, right? Time. The second M is the service time is Markov. K is how many servers you have, right? And of course, you look at how the servers or how the queuing, right, operate in the long run. But be very careful. This M right here, even though, right, it's kind of interpreted as Markov, it literally refers to the memoryless, the exponential clock. And like I said, memoryless and Markov is not exactly the same thing. Memoryless actually is stronger than Markov, right? But the MMK, you read this in the literature, right? They always tell you M means Markov. But if you just take that as Markov and you're like, oh, I have a Markov arrival, it doesn't work with that model because they really mean exponential clock. Okay, they mean memoryless clock. They don't just mean Markov. Okay, so that's a subtlety I want to point out. But anyway, let's continue with this on Friday. Okay.
Thank you, Professor.
Yep.
I have a quick question.
Sure.
So the last problem set, I think for this class is problem set number 10, correct?
Mm-hmm.
And
is it 9 or 10?
well, the
Oh,
homework due next week.
the homework 9, but problem set 10 because it corresponds to lecture 10. Yeah, go ahead. Yep.
Okay, yeah, homework 9, homework 9.
No worries.
How should
Homework
how would
9, right?
yeah, it's homework 9. You're right.
Yeah, but it's
How
confusing. Doesn't matter.
how would you expect us to prepare for the final exam? What are the topics like lecture-wise? Is certain content more emphasized? I'm assuming it's cumulative.
Yeah, so cumulative, let's say that, of course, the emphasis for this class is Markov chain, right?
Mhm.
So Markov chain will be more represented on the final exam than previous stuff, right?
Right.
But it's still, the previous stuff is still should still be there because of the whole cumulative nature of thing.
Right.
In terms of problem set, I will stop the problem set at the problem set 10, whatever, right? The recent one we just talked about. The reason is, right, I want to spend time exposing you guys to materials, right? Like, for example, process and hopefully Brine Motion in the next 2 lectures. And if we throw in problem sets, then we would not have time, right? So basically, I need 2 more weeks to do justice to these materials. So, yep, in terms of problem, that's it. That's the last cap of the problem set for this class. Does that make sense? Or does that answer your question? Or
That helps with part of my question, I guess.
okay, what's the other part?
So midterm 2, I think there were no proofs on it by my memory.
Yep.
I'm assuming there will probably be proofs on the final, and that it
So
would.
again, right, it still play on the whole framework of the problem set, meaning that, right, the problems you see in the problem set will have a chance to be on the final exam, right? The only thing I can say is the weight, right, or shift. Of course, the agenda is more on the Markov chain, and of course, like more on the things we haven't covered from midterm 2 or something like that, right?
Right.
They're all subjective, meaning that I'm not going to say, oh, I'm going to be very heavy on problem set 10, anything like that, right? There should be a spread. But yeah, I mean, any
But you would say
problems
everything is fair game from problem set 1 to 9.
from set 1 to 10, right?
Uh,
or whatever, right?
yeah.
Yeah, the most recent one, right? Everything on the homework is fair game-ish,
Okay.
with, of course, emphasis on the relevant materials in the spirit of the coursework.
Okay. Okay. And probably more emphasis on whatever wasn't covered in midterm, like whatever we learned after midterm 2.
Again, right, the word more should be taken with care because it's not like I'm going to pick all problems from that, for example.
Right, right. Because this is
Make no
final
sense.
exam. It's not like
Yeah, correct,
it's not
correct.
It's not like a third midterm. Yeah,
Yeah,
that
right.
makes sense. Okay. Okay, yeah, and it's 3 hours long.
Correct. 3 hours. You can use all 3 hours if you like. Yeah.
And we'll probably have a mix of proofs and computation with probably more computation.
No promise there. You should, again, like, I mean, the problems that we cover in the homework should give you a good clue on if
Okay.
if you're worried about proof, right? What kind of proof questions will be asked, or I'm not sure if you're worried about, like, I'm gonna ask some proof question that's exotic or whatever. That it's
Not necessarily exotic. Like, for example, showing that recurrence is a class property and it's not just
right. Okay, that's a fair question, and that's a lecture, right? That's in the
right.
lecture. That's not on the homework. Well, I'll make things easy by saying that the homework questions would be the model, right? I would,
okay.
unless I feel really inspired, I would not stay away, right?
Okay.
You know what I'm trying to say? So you, again, a confidence interval, right? Nothing's guaranteed, but with high confidence, you can just focus on the style of the question of the homework.
Sure.
Is that okay? And then, of course, it's very good that you should pay attention to lectures and everything like that. But I would go there as a last resort, as in, like, outside my confidence band, if that makes sense.
That makes sense. Thank you so much.
Sure. Yep.
All right. Bye, Professor. Thank you.
Sure.
Thank you.
Mm-hmm.